Welcome to the setup for facing and turning on the lathe. I know you're anxious to see some things get cut, but before we do that we have to make sure we set the speeds, feeds, and direction of the cutter all correct. So this movie we're going to look at a few things. We're going to review safety. You may be tired of hearing about this, but remember, you only get one chance to do things right. If you lose an eye, a finger, or maybe get killed, there's no going back and doing it the right way. So we have to learn the right way the first time. We're going to look at the types of cutting tools that are used on the lathe and how to install them properly. There's going to be a new thing that's going to go on the tool post. It's called the holder, and we'll show you how to put that and the tool on. Setting the spindle speed is very critical, and that will be demonstrated along with how to set the feed rate for the power feed, both for longitudinal feed, which will move parallel to the axis of the spinning part, and also the cross feed, which is going to move perpendicular to the axis. And finally, we'll show how to set the direction of the spindle so when you turn the machine on, it's spinning in the counterclockwise direction. Let's start with a safety review. All right, we're into our last movie with the lathe with Master Craftsman and Professor Don Howard, myself, John Waddick, just the kind of the pretty face behind this. So Don, we're going to do some turning and facing today. We're actually be cutting metal, so we have to be very careful while this machine is on. We don't want to have anything near, including your hands, near any of the moving parts or any of the power feed drives. Once again, remember, no hair. You have to be pulling that back. No jewelry, no long sleeves, nothing that's going to get caught. I mean, you have a fast turning part that's going to be merciless if it gets a hold of you. Okay, so you have to be very, very careful. And of course, remember safety glasses. Let's look at the very important points of safety. First off, safety glasses are a must. Even when the machines are not on, even when you're just cleaning up or walking in the shop, glasses do not come off. They don't go on your forehead. You got to put them right where they need to be, over your eyes. The most important thing around a lathe is to make sure nothing can get caught. You have some very fast moving parts. The spindle is going to be spinning. You also have the feed screw, which could catch something and pull you in. So hair is the number one. Let's start from the top of your head and move down. If you have long hair, it has to be tied back or constrained into a hat or hair netting. You can't have any loose clothing, no hoodies, no neckties, nothing that's going to get caught. Long sleeves are out. You need to have short sleeves, preferably. If you have long sleeves, you're going to have to roll them up. Jewelry, once again, no rings, no necklaces, no bracelets, no, none of that. Remember, hoodies, neckties, necklaces, anything that's around your neck could be a deadly instrument around a lathe, because that item can be pulled into the lathe and continue to restrict the blood flow and breathing so that in a very short period of time you could find yourself deceased. Finally, you have to make sure that you know where the spindle is in relation to yourself and also the feed screw. Those things are going to be turning, and if they catch anything, either a part of your body or anything you're wearing, they will just reel you in. And like I said, be very, very dangerous to you. So please be very careful. Next, I want to look at the cutting tool and how that works and how we identify it. All right, Don, from before, we've already have the part that we want to machine, which is known as the stock. It's in the collet, which is in the collet closure, which is in the spindle. Okay, I'm catching on.
Wow, you are good.
Okay.
You're a great student.
Well, thank you, Don. All right. I don't see anything that's going to cut anything. All right, this part is going to spin, but how are we going to take material away?
We have to use a cutting tool. So at this point, I have already pre-selected a cutting tool, and the reason I've selected this cutting tool, I have a multiple amount of clearance for both cutting edges, the primary and secondary cutting edges.
All right, what Don means by that is you see the big piece of metal I'm holding on to, and then there's up here a triangle. That triangle is the cutting surface. Now when he talks about clearance, you'll notice that there is some space between the thick metal and that triangular cutting thing. You see that both on the top face and that left face here, or your right face. All right, so that's what he means by clearance of the tool. Don is also demonstrating it here. Okay, so that is a desirable thing for our application today. All right, so we've got the clearance, and this is called a right-handed cutter.
Right. You would consider this a right-handed tool if I took my right-handed with the thumb extended. The primary cutting edge is your thumb is pointing at it, so we consider that a right-handed tool. I'm going to work from left to right. No, I'm working from right to left. All right, so keep that in mind. All right.
So we got a right-handed because you're right-handed, right? Is it like golf clubs? If I'm left-handed, I should go and get the left. Where's the left-handed one? There is one, isn't there?
Yeah, there's a left-handed tool right here. Here's a left-handed cutting tool. All right. If you look at this, my thumb, when I place my thumb under it, the thumb is pointing towards my primary cutting edge, and that would allow me to cut from left to right.
From left to right. All right. It doesn't have anything to do with someone being right or left-handed.
No.
Okay. Now, normally for our operations in Engineering 153, we're going to use the right-handed cutter.
Yes.
All right. So make sure you know how to identify the right-handed cutter. It's the cutting edge where if you look at it, your thumb is pointing in the direction of the point that it's going to be cutting. Let's review what Don talked about with the cutting tool. First of all, the cutting tool has two parts, the thick metal part, which I'll call the stock, and then the triangular part, which is the cutting surface itself. Now that triangular part is made out of carbide, and it's a very hard metal. It's good for cutting, but on the other hand, it's quite brittle. Excuse me, so if you drop this tool onto the floor, you could very well crack it. Once again, we talked about on the cutter that Don showed us, it has a triangular shape and it has clearance on two edges so that the triangular cutter hangs over the stock so that you don't have situations where when you're cutting, both the cutting tool and the stock of the tool would be touching your part. That would not be something we'd want to have happen. And finally, Don talked about there's right-handed and left-handed tools. So if you put a right-handed tool down on your desk so that the point, the triangular cutter, was on the top and facing away from you, it would be a right-handed tool if you place your right hand on top of the tool and your thumb points in the same direction as the point does on the triangular cutter. If, however, when you do this, that's not the case and the cutter is on the left, so you put your left hand on top of this and your thumb points in the direction that the cutter is showing, it's called a left-handed tool. In Engineering 153, you're only going to be using right-handed tools. Let's look at how to install the tool and the tool holder into what's known as the tool post. All right, Don, so we've got the cutting tool. We've got a tool post. Can we just put this on here somehow?
Yep. No, we can just set it there, but we won't get a lot of success with that. So what we need to do is we need to use a tool holder. Tool holder now will be assembled with your tool post. And once it's on there, you can see it still rocks. In order to tighten it up, I will pull this, and it locks up against that dovetail. All right?
Well, I don't see any tool in there yet.
Well, now I'm going to take my tool and I'm going to insert my tool into my tool holder. When I put that tool inside the tool holder, I butt it up against here. I'm going to grab my Allen key, which wasn't back in the rack. Tighten this up with my Allen keys.
Well, there's 3 Allen keys there.
Set screws, yep. So
3 set screws. You just crank them all.
I crank them all down tight, yes.
Okay.
All right. And the distance, from the further out you stick this, the worse off you're going to be. You got to think about vibration. The more rigidity is always going to be your friend when you set up. All right. So let's talk about that. When I got a part I'm sticking out here, the further I stick this part out, even though I can stick out 5 times the diameter. I want to keep it up as close as I can to my work holding device. The same with my tool bit. The closer I can keep it up next to my tool holder, the better off I'm going to be because I get less vibration. If this thing's sticking out, think of a diving board, right? The longer the diving board, the more flex I can get, right? And the further that thing will spring. So you got to keep those things in mind when you're running a lathe. Vibration's a killer on the lathe.
All right, so when you have a choice of having less sticking out of something, that's usually a better operation. But these look okay to you, Don?
Yes, rigidity is your friend. Remember that. So keep everything compact and tight.
All right, so you've tightened the tool into the holder. You've tightened the holder into the tool post by pulling on this. Now what?
Now I'm going to set up the tool for being the right angle to the part. Remember we talked about clearances on the primary and the secondary cutting edges. This particular tool is going to enable us to do 2 different functions. One is going to be a facing operation and the other is going to be a turning operation. And that's going to be because of the way the tool's been made and what clearances I have on the front face and the side face. All right.
So it looks like you probably have something set up pretty good, but Don's going to mess it up a little bit, show you like one way you wouldn't want to have it. He's loosened that up so now he can spin the whole tool post. So if he had it like this, notice that he's not cutting right with just the point. He's actually dragging the rest of the tool there as well. Don, this probably is not good.
That would not be good because I could never get a square shoulder. If I had to turn a diameter up to a face, we would call that shouldering, I would not end up with a square shoulder. I'd end up with a tapered shoulder because the heel of the tool is hitting, or the back end of this tool is hitting more than the nose of the tool.
All right, so the nose is the very tip. So Don's going to turn this because he wants just the tip to be touching. Okay, obviously you probably have a preferred angle. So he's got that just about like that. Notice that the nose is going to be touching. He's now cranking that down because he's got it the way he likes it.
Yeah, I don't have it touching when I'm tightening it down because I don't want to crack the carbide.
All right, so Don said he didn't want to have the cutter touching the part when he's cranking this down because this triangular piece is known as the cutter. It's carbide.
Right. It's very brittle like glass. If you turn the spindle on the wrong direction, if you smack it, you can crack it, and then it'll fall apart when you're machining.
So it's a very hard metal, Don, but with that hardness, you get embrittlement.
Yes.
All right. So this is a part that can be very sharp, can cut things, but could be very easily damaged. All right, so now he's got the angle set up. Don's now going to set up what's the proper height of the thing, and he wants to have that nose going to be cutting in at the part right along the center line that's going to go through the center of the part. Now, Don, it looks, what are you doing here?
All right. Like most of you engineers would recognize is the fact that if a line is tangent to an arc at its point of, yeah.
Yeah. Okay, I know what you mean, Don. What we want to do is, yeah. So here, the end result is this. Okay, I don't even understand it, Don. So let's just put it this way: this ruler's got to be vertical when held with the tool against that. In that way, we know we're going through the center.
Right. So my whole goal is that if my tool is hitting this right on center, my scale is going to be perpendicular at that point. So it'll be totally vertical to the bed of the machine. So if I come in here, I can see that this thing is tipping one way or the other, and then I can make the proper adjustments by loosening the tool holder.
Can you come in here, Jason, and take a look at what we're adjusting? So
loosen this, and then I can adjust the screw up or down in order to get this tool height. We call that our tool height adjustment correct until I get this thing to stand vertical.
And then he's using this thing, which is known as the cross slide, to move in. Are you happy with the way it is now?
Yes.
Okay, so the ruler went in, it's vertical, so we're at the correct height. We can check that later on when we do a facing operation. Let's review what Don talked about with installing the tool holder and then the tool into that holder. First off, you have to place the tool holder onto the black tool post. and you mate those two using the dovetail. It's pretty self-explanatory. Once you have the tool holder, you'll see how it fits onto the tool post pretty obviously. Now to tighten that tool holder down, you use the black lever that's on the top of the tool post, and you would turn that in the clockwise direction. You can then insert your tool into that holder. Obviously you want to have the cutting portion for the right-handed cutter. You want to have the nose of the cutter, which is the point that's going to be doing the cutting, pointing away from the tool post and toward the part. There's 3 set screws that have to be tightened on the holder to hold the tool into that holder securely. And Don mentioned that you don't want the tool sticking out too far because that's going to cause extra vibration and loss of rigidity. Don looked at or demonstrated how you could change the angle between or the angle at which the tool is presented to the part using the top nut on the tool post. He got the big box wrench and he loosened that up and then was able to rotate the tool post on the what's known as the compound slide. Once he got the angle that he liked, he then tightened down that nut on the very top of the tool post. The tool height is very important for getting good finishes and doing things properly. You always want the height of the nose to be at the center, the same height as the center of the part. And Don demonstrated that we could check the height by holding your 6-inch steel rule against the part with the nose of the tool. Now, if your ruler is not vertical when you hold it up against the part with just the nose, then you have to change the height, and you do that by loosening up the black lever on the tool post, and then you can move the tool holder up and down, and there's a little hand screw there on the tool holder that'll allow you to adjust the height. Once you get the height correct, then you'll want to crank down that lever, the black lever on the top of the tool post in the clockwise direction. Finally, bring the nose up against your ruler and hold the ruler against your part. If that ruler is perfectly vertical, then you are directly at the center of the part and you're ready to proceed. Next in line is we've got to set the spindle speed to the correct revolutions per minute. And Don's going to speak about that right now.
All right. We're not ready to cut yet, folks. We don't know which way our spindle's turning. We don't know how fast the spindle's turning. And we don't know which way our feed is going. There's all these levers over here. So Don's going to bring understanding to what is presently right now confusion on my part. Before we can set anything up, Don, we need to determine what our cutting speed's going to be.
Correct.
And I see on here that there's a formula up on the sheet here which says we should set our RPM to 4 times CS divided by phi. Now, CS is cutting speed and phi is the diameter of the part. Now, our particular part has a diameter of 1, so down here, this phi will just be a 1. Dividing by 1's easy, right? Do we need a calculator?
No.
No, okay. All right, but cutting speed. We're using aluminum, 6061 aluminum, to be exact. Where do we find a cutting speed, Don?
We find it on different charts.
Okay, so we can look that up. You could Google it, Machinist Handbook, a variety of places. All right, for aluminum, generally speaking, what would you say the cutting speed typically might be?
I would say start at 200.
200. Okay, so then if we do 4 times 200, that is 800.
Yes.
Okay, so that says that we ought to do 800.
That is correct.
Okay. All right, so our spindle should be at 800. All right, Don, where do I look in this maze of confusion to find my answer?
All right. Well, as we spoke about the headstock earlier, you'll find the chart that represents your spindle speeds in the upper left-hand corner, which is right here on your lathe. All right. As we look at this chart, we're going to look and see what is the closest thing to 800. Here we have 860. I don't see anything closer to it than that. So I'm going to set my gearbox up for 860 RPMs. All right.
So it doesn't have to be exact, Don. You just try to get the closest thing. Now, 860 is a little higher than what you just calculated, but I know the cutting speed has a range that could go higher than the 800, so we'll be okay?
Yes, the range for aluminum is a lot higher.
Okay. We're using a pretty conservative speed here.
Yes.
And that's due to just the inexperience of the students doing this?
Yes.
Okay. So a machinist who is doing this for production could use some different variables, but we're using 800. All right, so 860 is what we're doing, Don. What does the chart tell me?
All right, the chart tells you a number of things, right down to where do I need to set my high-low switch on my control panel, where my levers need to be set down here. I have two different levers we have to be contended with. So by looking at the chart, I got this column A, B, and C. I have this row up here, 1, 2, and 3, and I have this icon that represents my two-speed motor, which is up on my control panel, Roman numeral 1 and 2. So if I look at 860 and I look across here, I need to be in Roman numeral 2, which is my high range. I need to be in letter A, and I also have to have my lever in number 3.
Wow, this is kind of like Battleship. A32, hit.
Yes, you got it.
Okay, so let's start with the 2, Don. Where's that?
The 2, the Roman numeral 2 is up here on your control panel. All right, you can see you have a low and high range. Low range would be represented with the Roman numeral 1 on this chart. High range is represented with the Roman numeral 2, which is on this chart for your two-speed motor.
Okay, so that wasn't actually put nicely by the manufacturer. That was drawn with a Sharpie marker. I would have to recommend that the Sharpie marker do a little update on that so we can see it better.
Yeah.
Good enough. All right, so we got the 2. Don, how about the A?
The A you'll find down here on this lever is about waist high. You see your A, C, and B. We need to have that set up onto letter A. So I'm going to come over here, and this lever you just rotate. And if I can't rotate it, I can rock my spindle a little bit until it goes into gear.
All right, so just to review that, sometimes these levers can't be moved, and Don, because it's connected to the spindle, sometimes has to spin this, and you'll see him doing that throughout this operation. So, all right, so we've got A and 2. We have a 3 left.
Right. And this lever that was for 1, 2, and 3, you actually have to rotate it. There's a pivot point on this lever, so I have to pull this lever out. Okay? See how it pivots outward? If you don't move it outward, you're not going to get it to move at all. And you can rock the spindle all day, and it won't make a difference. So grab a hold of this lever, pivot it outwards, and then I can make a rotation. Now you can see I can't get it to go down. Going down is to the 1. Going up is to the 2, 3. And it's not going back in gear. It's still pivoted out. It didn't release back. I need to reach up in here, and I have to rock my spindle, just like Mr. Waddick has already spoken to you.
All right, so we have now set our levers 2, A, 3. Don, I see another lever here. What's that?
That lever there is for your feed direction. All right, I can go forward or I can go in reverse, or I can go forward or I can go in reverse. So you really can't determine direction until you see which way you want your tool to go. All right, this is called a feed reverse. I'm changing direction. It's just for changing directions of your feed.
Now, to make it a little bit easier, we're in Engineering 153, would you say most of the time going to be on this forward?
Yes.
Okay, that means that the feed is going to be toward the spindle.
Correct.
And the, what do you call this way?
Cross feed.
The cross feed is going to be in toward the part there. All right, so we're going to keep that there. Now, do you have to pull this out?
Nope, it's just a rotation.
Oh, I can even do it.
Yep.
I felt that. Okay. All right. Now, the other thing is to make sure that you're engaged, so the gears are engaged, there should be some resistance, and we should hear something.
Yep.
If this just spins loosely down, what's that indication?
Yeah, you may not be in gear.
Okay, now I turn the machine when I'm not in gear.
We're going to have a grinding sound. Gears not meshing. Could be ugly.
So then your instructor is going to come over here with a red face screaming at you and say, turn that machine off?
Yes.
All right. So just turn that, make sure you're engaged. All right. There's another lever, but I don't think we're ready for that one yet, Don. Okay.
But it's a great introduction to what comes next.
All right. It's a good introduction to what comes next is what Don said.
Spindle speed is really important to set it correctly, and Don mentioned how to do that. So there's a bunch of knobs and levers we have to be aware of. But before we do any of that, we need to know what is the cutting speed and therefore how to calculate the RPMs. So first of all, you'll see in a formula that's coming up something called CS, and that's called the cutting speed. Now, for our application and the aluminum we're using, Don has determined that 200 would be suitable. Now, cutting speeds for different materials and operations can be found online or in a machinist's handbook. There's going to be a variable phi, and you've probably seen this in your SolidWorks as well, that stands for diameter. And this phi has to be expressed in inches. For our particular part, our diameter is 1 inch. It's actually 1.003, but we're going to be close enough if we just use 1. The formula for spindle speed is 4 times cutting speed, that quantity, divided by the diameter in inches. So 4 times 200 divided by 1 gives us 800. Don mentioned that there was not an 800 choice on the headstock, and you locate the chart for the spindle speed on the headstock in the top left corner. The closest Don could find was 860 RPMs, and from his experience he knows that's close enough. So we then had to set the control panel knob at the very top of the machine to Roman numeral 2, and that Roman numeral 2 is written on the very top of the machine with a Sharpie marker. There's also levers on the headstock that had to be set to positions A and 3. So there's 2 levers and 1 knob needed to set the proper RPMs of the spindle. And finally, on the headstock, I should say it's actually the spindle, to make sure that those knobs that we have pulled and pushed on the headstock are properly engaged. You want to be able to turn the spindle. So the spindle should show some resistance. If it freely spins, it means things aren't engaged properly. Also, if while you're turning a lever, it just seems stuck and can't move, you may want to turn the spindle while you're moving or trying to move the lever, and it should get unstuck. So that's what you need to do to set your spindle speed. The other quantity that we have to worry about is feed rate. So Don's going to mention how to do that.
All right. So we've set up the spindle speed to be 860, okay, by using A23 with these up there and the high range. All right. What's all this business down here? Is it just to confuse people so that machinists can make more money?
No. It's to help us do different procedures on a lathe, from cutting threads, diametrical pitch threads, metric threads, module threads, all right? But the 2 charts that your engineering students are going to be in need of are your feeding charts, which are on the right-hand side of the gearbox. This is your gearbox area, and you can see by these icons. This is an icon, you got a tool bit, you got a part, and you also have an arrow indicating direction of this way along the longitudinal feed rate. And this other icon represents a feed. I'm going across the part, the end of my part. All right. So these are the 2 charts you'll be most interested in, and our recommended spindle speed or feed rate would be 5 thousandths per rev. So if we look through this chart, we're going to go in underneath our longitudinal feed. I just say you set it up for longitudinal, and you'll find 0.0051 is the closest thing we have to 5 thousandths per rev. So I'll look across, and it lines up with 6, and it lines up with E. I also have a letter M that I have to contend myself with. All right. So now you're starting to hear a familiar letter, a letter E. E was up here on your headstock, And what that does is it helps you keep the proportion between the spindle and the gearbox in relationship to one another. So when I do 5 thousandths per rev, that means my tool bit's going to advance 5 thousandths for every 1 revolution the spindle makes.
All right, putting that in terms that even I can understand, when we put the power feed on, and that's what this is going to be for, right, Don?
Yes.
Power feed. All right, so 5 thousandths per revolution means this carriage is going to move in 5 thousandths of an inch, 0.005, for every 1 revolution of the spindle. Okay. All right, and that, by using a power feed, we're going to get what Don's going to show us, going to get a nice finish. All right, so far we have we set the E?
We have just set the E. I rotated this lever up to where this lever lines up with the letter E.
Now, do I have to do the shake and bake here?
Yes.
Okay, yep, that looks like it's locked in, Don.
Yes. The next one, I have the letter M, right? Letter M is hidden underneath these 2 levers here, all right? So I want to make sure they're engaged, and they will be tipped to the left, or rotated to the left.
All right, so 2 M levers. Now there's a 6 in there, Don. Now we get into the complication. This looks like a truck gearbox or some kind.
Yes, it certainly does. It is a shift pattern, and you have a number of choices. You got 11 different choices, positions for your lever. You have columns and you have rows. You have 3 rows and the 4 columns. The 4 columns will have the number 6 is in my second column from the right going to the left. So in order to get there, I'm going to move this handle, raise it up to the center, and I'm going to rotate it over. All right? And if it doesn't go, what I would have to do is, if I got the situation where I can't get it in there now, all right, I just don't go run and get my instructor because I can't get it in gear or something wrong with it. Maybe you just need to do the favorite, rock the spindle. So I rock my spindle and I can get it in gear nicely.
So if a lever or this doesn't go, you just don't crank more and more force on it.
Correct.
Okay. It's usually solved by the rotation of the spindle. Okay. All right, Don, so we've put the M on, we've put the, which was it, E? And we did the 6. And we did the M. So there was the M, there was the E, and this was the 6. There's one other button here, Don, squiggly line, TPI, mod.
Right. Those are what that decides which screw you want to engage. All right. You have a feed screw and you have a lead screw. The top one is your lead screw. The bottom one is the feed screw. If we don't have this one spinning, you've got this lever in the wrong position. And when you go to hit your feed lever, nothing will happen. So you want to make sure that your feed screw is spinning by make sure this lever is all the way to the left, lined up with the icon that looks like threads.
Okay. So in our control panel over here, we've, I think, set all the things. We've got this engaged. It has some resistance.
A lot of information was given there about setting the feed rate, so let's review it and make some sense out of it. The feed rate is the number of inches that the carriage is going to move for every revolution of the spindle. Don has determined by his experience that a feed rate of about 5 thousandths of an inch, 0.005 inches per revolution would be a recommended feed rate for our situation. And you'll want to check with your instructor to see if this is indeed a good rate for your operation. On the lower part of the, well, I'll say the lower part of the machine on the left side, which is known as the gearbox, the feed rate chart is on the top left of that lower box known as the gearbox. And for a longitudinal feed rate of 0.0051, we saw from the chart that you had to set the various levers into 6E and M. And to do that, there was a pair of lower levers on the gearbox that we set to M, so both of them were turned to the left. Then there was one lever on the headstock, which was above the gearbox, and we set that to E. There's a complicated truck type shifter on the lower part of the middle of the gearbox, and Don set that to a 6. And when doing these different operations, you may have to turn the spindle to get things to engage properly. Also, when you're done with all this, you should also spin the spindle to make sure that there's some resistance and it feels like things are engaged. Then there's also a feed type selector on the right of the gearbox, and you have to set that to squiggly line. Okay, by setting it to squiggly line, that means that the power is going to be engaged to the lower feed screw. If you put it onto any of the other two choices there, then you would be sending power to the lead screw, which is on the top. The last lever that needs to be addressed is the one for the direction of the feed, and you want to set that to what's known as the forward direction. This lever is on the right side of the headstock, and you'll see this symbol, which is squiggly line and left arrow. So you want to be on that setting, and that's actually pushing the lever to the right and selecting that. That's what entering 153 students will be using, always a forward direction. Next, a fairly simple operation will be covered quickly, and that is setting the spindle direction, either clockwise or counterclockwise.
All right, we're going to just about ready to fire this up. Jason, our cameraman's going to move over, and we want to make sure that our spindle is going toward us. Is that right, Don?
Yes, normal. We would call it to normal direction. You want the material to rotate into the top of the cutting tool or into the cutting edge. So it's always important. The way our tool is set up now with cutting edges on the top as we're looking down, and our tool's material needs to rotate into it. So it's going to want to rotate towards us.
All right, so when Don fires this up, there's a couple things we want to check. We want to check to make sure that this spindle is spinning toward us, or as viewed from your camera, it'd be counterclockwise. And we're also going to want to make sure that the feed screw is turning, okay? And if that's not the case, we're going to have to check something. Okay, so Don is going to engage this. There's two ways. He first has to pull this, this lever, this button out. All right, he pulls that out. And if he goes down, notice the feed screw is turning, and I can't tell which way the spindle's turning, Don. So what should I do?
One thing you don't want to do is go up here and reach in and grab the spindle and see if I can feel which way it's going. Very dangerous situation. You can't see the holes that are inside that collet closure or that chuck. And what will happen, you can get your finger stuck in there and rips the finger right out of joint, and you end up losing a finger. So don't do that.
All right.
Jog the spindle. All right. So I shut the spindle down. As I shut the spindle down, I can jog it very littly and see the direction of the spindle is rotating.
All right. So you can do its jogging. Pull it and push it down. You can see that it goes in the right direction. Let's just reiterate one thing here, folks. That lead screw, okay, I'm sorry, that feed screw, because this is the lead screw, this feed screw and that spindle are turning. They will suck anything in that they can grab, okay? And you can get pulled in and hurt or killed here. That's why you're not going to have any hair, you're not going to have hoodie straps, you're not going to have jewelry, you're not going to have long sleeves. You have to be very, very careful with this machine. It's probably one of the most dangerous machines in this whole shop. So take that seriously. All right, so Don, we have now the speed. We know that if we pull that down, we're getting the correct rotation.
Let's review setting the spindle direction. The normal way we would want the spindle to turn would be counterclockwise. That way when we're doing an operation such as turning, the material of the part is turning into the top of the cutting surface. And I just mentioned that feeds the part into the top of the cutter. All right, to make the spindle go in the counterclockwise direction, there's a black knob over by the red emergency stop. So you'd pull out that black lever and then you push it down. That would cause counterclock rotation. If you pulled it out and pushed it up, you'd get the reverse direction on the spindle. Now you want to check the direction of your spindle by pulling the black lever out and pushing it down just momentarily, and that'll engage the spindle just for a short period of time and turn the spindle at a slow speed so that you can see that it is indeed going the way you want it. Don emphasized you never want to check the direction of a live spindle that's moving fast. So if it's moving so fast you can't tell which way it's going, that means it's going so fast you can't see the different cam nuts and things that are on that spindle. You put your hand there, your finger can get caught in one of those cam nuts and it's going to get ripped off your hand and probably going to break it right off and probably even break your hand. You never want to touch a spinning spindle and never want to touch a moving part, and you don't want to touch the spinning feed screw either. We're ready to look at the face and turning setup questions. First question. List the things that are dangerous to wear around a lathe. And then, what two parts of the lathe can pull a student into the machine? Number 2, how is the height of the cutting tool adjusted? How does an operator test to be sure that the cutter height is at the center line of the part? Third says, compute the proper spindle speed in RPMs for a part with a diameter of 30 millimeters. That's 30 millimeters, so be careful. Question 4 says, where is the chart for the spindle speed located? Followed by a follow-up question, which is, where is the chart for the feed rate located? Last question, what must be done to turn the spindle on so that it rotates in the counterclockwise direction? And also, what is the proper way to check the rotational direction of the spindle? What must you never do to check the rotational direction of the spindle? Thanks for tuning in, and we'll see you on the next movie where we actually cut metal on the lathe. It's going to be so cool, you don't want to miss it.